Now next I will show you a small battery pack and the major components of a battery pack. And either it is small or big, these components remains unchanged. More or less you will find all those components there. The first one is battery cells. Now for a battery pack, battery cell become a component. When we do series and parallel connections, generally cells are made of, outer casing is made of metal except pouch cell, where it is made of some polymers. If you talk about cylindrical cell or if you talk about prismatic cells, in both the cases the outer casing is generally made of metal. In prismatic cells, that smaller cells which we use for cell phone or in laptop also is made of polymer, but if you talk about EV application, most of the cells are made of metal. What happens? There are two terminals, positive and negative. One of the terminal, either positive or negative, mostly positive, would be connected to the cell body or directly embedded on the cell body itself. So your cell is always at some potential, either it is positive or negative depending upon the terminal. So when you are putting two cells in series, so there is always a chance that current can make a local loop, current flow can make a local loop. To prevent that, we provide an insulation. Now problem with the insulation is that generally insulation, when we talk about, the thermal conductivity is also very low, obviously electrical conductivity has to be low. But what we want? Heat to be dissipated. But if I am insulating a surface, that means not much of the heat can escape. We want to prevent the charge movement, electrical charge movement, but not thermal. Sometimes it is also desirable to thermally isolate in the case of events like thermal runaway or short circuits where cell can get heated up, it should not impact others. So sometimes we require that also, but most of the time what we require is that it should be able to dissipate the heat from all the direction, but generally that does not happen if we use insulation. But our primary purpose is there should not be a local loop of current, there should not be a current leakage. So we provide the insulation after every parallel cells. If I have 4 parallel cells and then another 4 parallel cells and these 2 are in series, I provide an insulation between these 2, so that there should not be a leakage current. Base plate, it is responsible for holding all the cells together. It is responsible for any external factors like vibrations beyond control, still protect the cells. Side strips help fixing together the end plates. These are the end plates here, this. Why end plate is required? I will talk later. It needs to exert some pressure on the cell so that bulging should not happen. It increases the life of the battery pack. End plates, just now I talked, why we require is basically to constrain the cell movement, one thing, base plate, end plate and side strips. The basic function of all these 3 are constrain the cell, put some pressure over the cell surface, so that, and that is a uniformly distributed pressure, so that we can increase the life. We will talk it later how to increase the life and why it is needed to put some pressure. And the side strip holds the end plate together with some pressure. The cold plate is required to maintain the temperature within the optimum range. Bus bar holder. Now we are putting the bus bar, now we are connecting in series and parallel, and that is done by bus bar. And then bus bar should not move, it has to be constrained. If it is moving, that means there is a chance of short circuit. So we provide a constraint, that we say bus bar holder. Now the bus bar is needed for series and parallel connection to efficient flow of current, efficient flow of energy. Thermistor and voltage sensors. So thermistor measures the temperature, log into BMS, and then BMS takes action based upon the temperature. Similar way, it also logs the voltage, because the voltage is varying between some limit, and with the voltage varying, we know what is the charge and discharge condition of the battery. Wiring harness is required for, again, the efficient flow of energy and the efficient flow of signal, both in and out, bidirectional. BMS is the heart of a system which communicates with within the pack temperature, voltage, current flow, and outside like motor and controller, drivers. The outer casing is again required to prevent from environmental conditions. If somewhere it is raining, water should not come inside. If it is dusty environment, dust should not go inside, because what happens, if water comes inside, you may find short circuit condition there. If the dust comes inside, the resistances of all the contacts like bus bar is welded with or screwed with cells. If the dust deposit happens here, resistance increases. If resistance increases, what will happen? The higher heat generation and the lower efficiency, energy flow. Or the condition like crash, it should be able to protect my inside domain, cells, holders, and all those things. So that is work of outer casing. So all together, battery cells, thermistor and voltage sensor, insulation pad, base plate, cold plate, outer casing, bus bar holder, side strips, wiring harness, end plates, and BMS. This all things together forms a battery pack. If the battery pack is bigger, this is around 2 kWh battery pack. If battery pack is 20 kilowatt, the parts remain same. Part does not change. The length, width, thickness, rating would change. Any question till now, which we will talk now. So the question is that in battery pack, the cells are in series and parallel. Yes, both are there, which we will talk now. There are mechanism. Yeah. So the question is, what causes battery to be discharged in the event of crash? So actually, we don't want to be caused. Basically, what we want to put a mechanism during the crash situation. My battery should be able to dissipate the energy as fast as possible. So some high value of resistance in parallel path, which get connected by BMS command if such event is about to happen. So what happens, that whatever the energy stored because of charging gets at least dissipated immediately. Some people make it in 5 minutes, some people make it in 10 minutes. Somewhere we don't put, for like a smaller pack like this, we don't put, but let's suppose a bigger pack, 100 kilowatt battery pack is there. If there would be a fire hazard or thermal runaway case, so at least in that case, whatever the energy is stored, electrical energy is stored, we do not have to worry if we are able to discharge it quickly. So, only thing which we need to worry about that time is chemical energy. So, it is a choice of a pack designer and requirement of the vehicle, different standards and this, but mostly it is resistive dissipation. In this pack we have not shown that particular thing, but can be.
And heat evacuation only happens from one face, the bottom?
Cooling can happen at any place where you have exposed surface. In fact, in between cells also you can put the cooling plate. It is all based upon the requirement, how much thermal energy or heat load is coming up in the battery pack. So, the question was the base plate is cooling plate is always kept at the bottom. No, it can be kept at the proper location during the designing, and also depends upon what is the heat load of the battery pack, what is the environmental condition we are going on.
Thermal runaway can only happen during charging or while working also?
It can happen at any time.
So, if a car is driving and there is a thermal runaway, car will halt itself or it will give a warning in that?
No, but before thermal runaway, lot of events happens. One of the very first event which you can measure easily is temperature start rising up. It does not happen certainly at 35 degree, it never happens. So, there is a threshold 90 degree or 125 degree or 150 degree or 200 degree, like for NMC cells it is approximately 150 plus degree, and beyond that it is very difficult to control.
There will be some kind of warning before.
Yeah. So, now we have put here thermistor. So, it will detect if there is a temperature gradient which is beyond a specified limit. Let us suppose my temperature is rising up 10 degrees C per second. However, I have built it for only 2 degrees C per second. So, this information will go to BMS. Now, BMS will have all the processing capacity and it will detect where it is going. Then it will immediately shut off. In many of the battery pack, it will start discharging the cells in such a way that other cells, so that my energy content of the pack becomes minimum as possible. Especially if you go to storage application, in EV application, you have a fire suppressing system also that gets activated. However, saying that now it is going to happen thermal runaway, it is very difficult. There is no clear cut physics for that one till now, or physics has not been understood clearly till now. Now, we are going to start mechanical design. Till now it was a background for a battery pack design. Now, we are going to move ahead with the mechanical design. So, what are the important considerations for a mechanical design? In the right side picture, if you see here, battery pack, and this one is the battery pack of Nissan Leaf. The most important part of a mechanical design is material selection. Which material you should take? What are the criteria for material? It should cost us less, easily available, should have good to great strength, not hazardous type, means not poisonous. So, we will talk in the next slide what material selection, how do we do a material selection. The second one is base plate design, over which we stack all the cells together. we accommodate the total cells. Then we also have to worry about cell movement. We do not want cell to move, because that is a primitive block of a battery pack. So, we constrain and control the movement of the cell. Uniform pressure all over the cell surfaces, that helps in prolonged life, that increases the life of the cell. In chapter 4, when professor was talking about cells, he has also shown some pictures of how the cell get bulge during the charging and discharging cycle. We do not want that bulge to happen, because that reduces the cell life drastically. Material cost optimization. I can have a material which is great in strength, but my pocket will not allow. I have another material which has good strength and also fits in our budget. Then outer casing design, outer case design for overall protection. Bus bar design. Packaging constraint. A vehicle space is in premium. And it may not be a regular surface like a rectangle or a cylinder. If you see the pictures here, you see it is a quite regular shape here. But if you see here bottom one, this portion is rectangle, again this is rectangle, but height is not same. It is a packaging constraint, this is the space available. Now, at the last row, if you see, the height is quite elevated. So, within here, so within one pack, the profile is not same, it is a different for different stacks of the cell. And why that has happened? Because people will love to go for a rectangular or cuboid type of shape, it is easy to construct. It is because of the packaging constraint, because that is the only space available in the vehicle. Because again vehicle has to take care of lot other things. It has to package motors, controllers, auxiliary systems, wiring harness, cables, seating arrangement. Who buy the vehicle? The person like me and you or some human. What they need? If I am sitting, I should be relaxed. So, that becomes always first priority. And after that, whatever space is available, that is allocated to the subsystems like battery pack, motors, controllers, auxiliary systems. So, the packaging within the packaging constraint, I need to make my battery pack. Let us move ahead and let us start making the pack. So, cell is the building block for any battery pack. I am showing you a picture of 15 Ah cell. The voltage is 3.65 volt for this individual cell. Current rating is 15 Ah. The length of this cell is 17 mm. Why I am putting length of this cell? Because we are going to stack this cell. Breadth 65.4 and height is approximately 126 mm. Let us go back to MP-NS theory, M parallel, N series. So, if I am putting everything in parallel, all positive terminal connected together, all negative terminal connected together. What it does? It increases the AH. So, that many times the number in parallel, that many times AH will get added up. So, here 8 cells are in parallel. Now, each cell capacity is 15 AH. So, this 8P1S configuration, what would be the current rating? 120 AH. 15 plus 15 plus 15, 8 times. So, that is nothing but 8 into 15, so 120 AH. We say capacity of the battery also. What would be the voltage now? Voltage is 3.65 volt only, because we have connected all the cells in parallel. Next move. The second configuration is series configuration, where every alternate cell positive and negative terminal is connected. You see, positive, negative, positive and negative, and then this side again positive and negative. So, this configuration is known as series configuration. In series configuration, what happens? Voltage adds up. Now, what I am saying, one parallel, because I am taking only one cell in parallel, other next cell is in series, again next cell is in series. So, what happens here? Voltage add ups. Voltage add up means my one cell voltage is 3.65 volt. Now, I have put 8 cells in series. So, 3.65 plus 3.65 up to 8 times. So, I can simply put it 8 into 3.65. This is 29.2 volt. Now, let us see if I put 8P8S. So, what would be the current capacity? When I talk about current capacity, it is 1C. So, what would be the current capacity and what would be the voltage? If I put 8P8S, so if I put 8P8S, 8P gives me 120 AH and 8S gives me 29.2 volt. So, now if I consider this as a pack, so now my pack is 29.2 volt rated at 120 AH. You multiply these two, 120 into 29.2, for sake of calculation take 30 volt, it is a 3.6 kilowatt hour pack. You multiply voltage with the current rating, it will give you the capacity, pack capacity. It is a 3.6 kilowatt hour battery pack, where my current rating is 120 AH. Whenever I talk about current rating, it is at 1C, and my voltage is 29.2 volt. I can make any voltage, any AH of the multiple of this particular cell. If I have other cell which is 10 AH, again 3.6, and if I need 40 AH battery pack, so I have to put 4 cells in parallel. If I need, if I put higher capacity cells, then number of parallels will come down if I have to maintain the same AH. Yes, the cell in chapter 4, when professor was talking about the cells, he was talking about 3 AH, 8 AH, 14 AH, 15 AH, 13 AH, 50 AH, 55 AH, 24 AH, these all are form factors. However, except cylindrical cells, not all cylindrical cells, but most of the cylindrical cells has a standard shape or form factor. If you move ahead other than cylindrical cells, let us suppose for prismatic cells or pouch cells, every manufacturer has their own form factor. So, and obviously it is not a continuous increment like 1 AH, 1.1 AH, 1.2 AH, no. There are certain AH cells available. You can have 15 AH cells which is available, you can have 24 AH cells, you can have 50 AH cells, you can have 55 AH cells, you can have 60 AH cells. Yes, corresponding, there is, that's what I said, form factors is not constant. For this particular, that's why I am giving you this all the dimensions as well as voltage as well as current. This is one particular form factor. I change the cells, let us suppose I bring the cylindrical cells. The question is that do we have the same form factor for all the cells? No. Form factor is generally standardized for cylindrical cells, but for pouch cells and prismatic cells, every manufacturer has its own form factor. So, depending upon the requirement, you need to select a manufacturer form factor, and then you need to see that who has this form factor. If you have, let us suppose 5 gigawatt hour capacity requirement or 1 gigawatt hour capacity requirement, a manufacturer would be happy to align with your form factor. But let us suppose you want 100 kilowatt hour battery pack or 1 megawatt hour battery pack, because in that case you have to utilize what is available form factor. So, form factor is very important. So, based upon your packaging constraints, the capacity requirement, energy requirement, you have to select out of available things, and or you can make your own form factor, you can demand your own form factor if your requirement is very large, because cell manufacturing process is very costly affair. If you see in the chapter 4, material is 30-35%, the cell manufacturing is 30 to 35%, and the pack with this all mechanical things what we are talking now and what would be talking add up around 30-35%. So, 1/3 of the cost of a cell or a battery pack is basically cell form factor or manufacturability. So, what most of the people demand? They make a form factor to that requirement, and if you have a very low requirement, then you have to select out of that. If you have a very high requirement, you can enforce your form factor.